Every time you stream a movie, send an email, or just scroll through your feed, you're tapping into this massive, hidden world of digital infrastructure. And at the very heart of that world are data centers. Their lifeblood? A constant, totally uninterrupted flow of electricity. So, we're going to pull back the curtain on the incredible engineering that builds a literal fortress of power around them, keeping our digital world online no matter what. It's a terrifying thought, isn't it? I mean, for our world today, a power failure at a major data center isn't just some inconvenience. It could mean losing access to critical services, financial data, communications, all of it on a massive scale. But the real danger isn't just in a long blackout. That's right, just a millisecond. For the super sensitive IT equipment inside these places, a flicker of power that lasts just a few milliseconds can be absolutely catastrophic. It can corrupt data, crash entire systems, and cause this horrible ripple effect of failures. So the real question is, how on earth do you build a system that guarantees zero interruption? Well, you build a fortress. Not with walls and stone, obviously, but with layers and layers of redundant power. It's this incredibly sophisticated, three-tiered defense system, and it's designed to make sure that the servers inside never, ever lose electricity. Okay, to really get how this system works, think of its two main backups as different kinds of athletes. On one hand, you've got the massive diesel generator. That's your marathon runner. It can provide power for hours, even days, just as long as you keep feeding it fuel. Then, on the other hand, you have the UPS, which stands for Uninterruptible Power Supply. Now that's your sprinter. It provides this huge, instantaneous burst of energy right from its batteries. Each one has a very specific and absolutely crucial job to do. So, before that power ever even reaches a server, it has to go on a bit of a journey. It shows up from the grid at a really high voltage. In this case, we're talking 15,400 volts, which is great for traveling long distances. But then, a series of transformers have to step that voltage way, way down to make it safe and usable for all the delicate electronics that actually run our digital lives. All right, so we've designed our fortress, and we know who our key players are. But how does it actually hold up under attack? Let's go ahead and simulate a blackout and see what happens the second the main power from the grid gets cut. On any normal day, it's a pretty simple, calm flow. Power comes in from the utility, gets transformed, it passes through the UPS, which is just sitting there on standby, and it feeds the servers. Everything is stable, and all those backup systems are just waiting. And this, right here, is the core promise of the entire system. See, it's not just about having a backup plan, it's about creating a transition so seamless that the servers don't even have a clue that a failure has happened. So let's see how it delivers on that promise. Okay, let's start with something small, like a momentary power flicker or a sag from the grid. The instant the system detects any kind of irregularity, the UPS batteries kick in. And there's absolutely zero gap in the power supply to the equipment. It is completely, totally seamless. And when I say instant, I really mean it. The detection and the switchover to battery power all happen in less than 4 milliseconds. Now, to put that in perspective for you, a single blink of a human eye takes about 100 to 400 milliseconds. This system reacts dozens of times faster than you can even blink. It's incredible. Okay, now for the main event, a total grid failure. The moment the grid goes down, our sprinter, the UPS, instantly takes the load, just like it did before. But at the exact same time, it sends a signal to our marathon runner, the diesel generator, to start up. The generator just roars to life, and once it's running at full, stable power, the system smoothly transfers the load from the UPS over to the generator. And this just brilliantly shows you the crucial role of the UPS. That whole startup sequence for that massive generator, it takes about 10 to 30 seconds. That's the critical gap. The UPS's entire job in this whole scenario is just to sprint for about half a minute, perfectly bridging that gap to ensure the power never, ever stops. But what if the problem isn't outside the data center? What if it's inside? A short circuit or an equipment overload could be just as devastating. And that's where another layer of protection comes in, this kind of internal safety net. Think of this like security checkpoints in a building. You have these massive circuit breakers guarding the main power entrances, and then you have progressively smaller ones protecting each floor, each room, and finally each individual server rack. This hierarchy is so important. It means if one single piece of equipment faults, its specific breaker trips, and that immediately isolates the problem. It doesn't cascade and take down the entire system. So what's making this whole complex dance happen so fast and just flawlessly? Well, the conductor of this whole orchestra is the automatic transfer switch, or ATS. It's like a watchdog, constantly monitoring the quality of the power. The second it senses a problem, it orchestrates that entire handoff between the grid, the UPS, and the generator. All of it, automatically, without a single person needing to even think about flipping a switch. So when you put all of these pieces together, the redundant sources, the instant failover, the layers of protection, you get a system that's designed for one thing and one thing only: absolute reliability. So let's recap the blueprint for this power fortress. At its very core, you've got that uninterruptible power supply, thanks to the UPS and generator duo. That's all supported by multi-stage voltage conversion to make the power safe and usable. The entire thing is managed by automated transfers, which gets rid of any risk of human error. It's all protected by that hierarchy of circuit breakers to isolate any internal problems. And finally, the whole architecture is scalable, so it's always ready to grow. This, right here, is the recipe for our always-on digital world. So, we've built this incredible fortress to protect our data, a system that guarantees the always-on world that we all depend on now. But that kind of leaves us with a bigger question. All of this resilience, all of this backup power, it has a massive energy cost. What does it truly take to power the very infrastructure that powers our lives? That's definitely something to think about.